Okay, so students, now in this video I'll show you how we can measure the dispersion in an optical fiber. So, but before we start, I'd like to mention that in this experiment, from this experiment onwards, we'll try to use different circuit segments that this light runner is having. So, for example, in this particular experiment, we'll try to utilize these two circuit segments, which are called optical couplers. So you can see that there are two input ends of this coupler and one output end. It means that if the lights from two isolated sources are inserted into the two input ends of this coupler, then at the output end you'll get both the sources simultaneously. And if we connect this output end of this coupler to the input end of the second coupler, then at its output both the sources will get separated. Okay, now what do we mean by dispersion? So it means that if we have two wavelengths which are separated by 1 nanometer, and if both of them propagates through a 1 kilometer long fiber, then the temporal separation of them at the output end of the fiber will give you the dispersion. So if the temporal separation is 10 picosecond, then the dispersion of this fiber is 10 picosecond per kilometer per nanometer. Now the standard fiber is also having the similar kind of dispersion, which is tens of picosecond per kilometer per nanometer. Now the kind of scaling that this inbuilt DSO of this light runner is having, it's very difficult to measure such a low temporal delay. So okay, so the dispersion that I mentioned actually is at 1550 nanometer. Okay, so but then it's very difficult to use to get such kind of dispersion using the present scaling of DSO. So what we will do is the following. So we'll choose two wavelengths which are well separated, and we'll make use of these optical couplers. How? So in this experiment we'll choose two wavelengths, like one will be at 1550 nanometer, the second wavelength is at 850 nanometer. Okay, so 850 nanometer is second wavelength. Now both the inputs are now getting connected to the two input ends of the coupler. So one is connected to the 1550 and the other is connected to 850. The output of this coupler is actually connected to one of the input of a fiber spool. Now we have three spools of lengths 1 kilometer, 2 kilometer and 3 kilometers. So altogether you have 6 kilometers long fiber. Now each spool is having two ends. Okay, so we'll connect this output end of the coupler to the one input end of the spool. The other end has been connected to one of the input end of the other spool. So like this we actually interconnected all the spools, and the light from the final spool is connected to the input end of the second coupler, and at the output of this coupler we'll get back this 1550 nanometer and 850 nanometer. So we connected those two sources to their respective photodetector. Okay, and to see the respective waveform, we connected the adjacent port to the two different channels of this DSO that is inbuilt with this light runner. Okay, and then what we did is that we need to freeze those two waveforms. Okay, we need to freeze the frames, and from the freeze frame we can actually measure the separation of their arrival time. Okay, so now I will show you how the waveform will look like. So you can see that. So I'll show you that this green curve corresponds to the source which is at 1550 nanometer. The yellow part corresponds to the source at 850 nanometer, and the difference of the arrival time is something like this. So how will you measure it? So here I think you can see this scale, right? This is the time base, and you can measure this using this tab. So you can see this is actually the measurement tab. There are three rows, which is first one corresponds to voltage channel 1, voltage channel 2 and time base. Now since we need to measure the temporal delay, we need to make use of this time base. We need to click on that. Once you click on this, you will need to choose the points between which you need to measure the time delay. So once you choose this, you'll get these cyan lines. Okay, and then if you can click on this calculate, you will get the temporal delay between these two. Okay, but here since we are doing it in an online mode, what I will do, or I'll ask you to do is that I'll send you this snapshot. You need to make use of the time base of the inbuilt DSO to measure the temporal delay between these two lines. Okay, and from this delay you can actually measure, you can actually get the dispersion in an optical fiber. Now since here you have chosen 6 km long fiber, the separation will be higher. If you could have chosen 1 or 2 kilometers, the separation will be low. So but however the dispersion value of this fiber will be similar. So I'll send you 2 or 3 snapshots. You need to measure the dispersion, and then from that you need to evaluate the average dispersion value. Okay, so that's it. Thank you.